Now, one of the ROS packages I've been looking into is the part of the image pipeline. It's stereo image proc, or stereo image processing. So the ROS package will take the individual images from both left and right cameras, and it'll do some basic video processing in the form of resizing the images, rectifying them to remove the lens distortion. But you can do some pretty cool things with the image pipeline. It may not be apparent at first, but down the line when you get into things like SLAM or VSLAM, you can do some pretty cool things with your robotics vision. So we're all kind of just in the perception land right now. I will maybe touch on VSLAM a little later on. The main thing is you have to get the perception part right to get something cool and awesome and an open research topic like VSLAM. With stereo image proc, you want to probably start with a synchronized stereo image pair. For example, you have two of these cameras and you're able to connect them to your board or your computer. So you're going to have to find a way to synchronize them. For this video, we're going to assume that you have a synchronized stereo image pair, and they're both on the same plane horizontally, and they're not turned inwards. They are perpendicular to the board they're mounted to. So the first thing that you're going to have to do, and if you buy a RealSense or something like the Z camera, basically you buy an all-in-one kind of stereo camera solution. You can assume they've probably taken care of most of this for you in their ROS packages. But for this example, I had to find a USB camera package, modify it for ROS 2, and because this camera implements just one image, it outputs one image that's not split. I had to split the image into their own image topics, and that took a little bit of work. So once you've got your camera package, you're able to see that you have a left and right raw image. You've got camera info messages for each camera. The next step is to calibrate. So, friendly reminder, never leave home without it. You're going to have to use one of these, the checkerboard pattern, to calibrate the stereo camera image pair. Now, I've read online that you don't want to individually calibrate your camera. You want to calibrate both of them at the same time. So run the camera calibrator on the whole stereo image pair. So you've got a synchronized stereo camera pair. You've got some sort of ROS package that can interface with it, be it something like a USB camera package, or if you're running a Jetson Nano, and you have two cameras that have interface with the Argus lib. You could do that too. If you have a RealSense, that's kind of, it's a given. They have ROS packages for RealSense, and so same with the Z camera. I think it's another popular one. So after calibration, you can load up those ROS packages and run the image pipeline. Now, for my example, I'm using a Jetson Nano, so I'm going to use the Isaac ROS version of image pipeline. So it assumes some of the same basic topics be published via ROS 2 Foxy, which is what I'm using, but it builds on it with the image pipeline. So the Isaac ROS has some CUDA libraries, particularly the vision processing. I think it's called VPI. I forget the acronym name. Anyway, so you have the VPI library that's kind of in the back end. So that kind of abstracts a lot of the stuff away. But when your two outputs from stereo image processing is really the point cloud and the disparity map. So the disparity map could be used to compute depth. So it may be useful if you're trying to do some sort of obstacle distance. The theory goes that as your distance increases, your disparity diminishes, right? Because if you think about it, If you're looking at an object far away and you close one eye, you can't really see a lot of difference between left and right, how your left and right eyes perceive it. But if you have an object up close and you close one eye, there's a definite disparity between what your left eye sees and what your right eye sees. So there's an inverse relationship between disparity and distance. On to point clouds, which is probably more interesting to most people. The point clouds that you get from the stereo image pipeline, you could use for mapping. And that's the fun part. We're getting into the fun stuff that most people want to know about. And that could be used in VSLAM as well. So you've got some outputs from perception that are pretty useful. I would say the point cloud more so, probably more used. Then you get into kind of the nitty gritty of disparity image processing. So let's go down that rabbit hole. So there's two sort of main algorithms that ROS, you can use in ROS. There's block matching and semi-global block matching, or SGM. Now SGM is a little bit compute intensive. From my research, the SGM algorithm kind of slides a kernel across an image, which is really your disparity range. And it sort of introduces a cost map for kind of matching what's in one image to the other image. So it is a little bit compute intensive, but definitely I think it's going to produce better results in the disparity map. If you're very resource constrained, I would probably use the block matching instead of SGM. But for this example, we're using the Jetson Nano, which should have enough processing power. However, I'm not really sure what algorithm the BPI is using. I'd have to dig into it further, but some of Nvidia's libraries are kind of closed off. They're closed source. You can't really see much. You pull in the library and you call some functions in that library, and then you don't know. Then we go down the rabbit hole of point clouds. So I noticed with the Jetson Nano and Isaac ROS, by default, if you launch the Isaac ROS stereo image pipeline, it's going to do a grayscale point cloud. You've got to set a parameter that says, hey, no, I want color. I want a colored point cloud, not a grayscale one. So I did that and got some interesting results. So you've got your outputs as your disparity map and your point cloud, and you say, well, what's next? So there's a couple things you can do. You can take, at least with the Jetson Nano, you can take your stereo images and feed them into VSLAM, which is what I've done. At least some basic visual odometry, as I don't have an IMU on this camera. But if you're running a RealSense that has the stereo camera pair and the IMU, you're pretty much set. And actually Nvidia assumes that you're running RealSense because they have some components that's in the launch file for the RealSense. For the Z camera, they have their own packages, I think, which also feed the IMU as well into it. So you can get the visual odometry or visual inertial odometry if you have an IMU. The other thing that you can do is you can do VSLAM, or really VSLAM sits on VIO. So the odometry is really just going to compute your pose in space relative to your starting position. But it's kind of like walking down a long corridor without really knowing, well, what was behind me. With VSLAM, you sort of have like whereabouts of, hey, where you've been, and you sort of close the loop. It's kind of like navigating a shopping center and then coming back to the starting point with knowing what aisles you went down and what products you saw in those aisles. That's the best summation of SLAM I could think of. So with VSLAM sitting on top of VIO, you can do some pretty cool stuff too, because then you get into localization and mapping, navigating your environment. You get into, you're crossing the boundary from perception into navigation, and that's a whole different video, because navigation is its own can of worms, right? You really gotta, at that point, have everything in perception going right for you. But that's pretty much it for this video. Give me a thumbs up if you found this helpful. Maybe one day I'll do a VSLAM video. We'll see. Out.